Shoot, I really liked everything I was saying so far. So, okay, well, anyway, we're recording. This is a portion of the 6.2 notes starting on page 2. So what we're doing is we're redoing these partitions. So a width of 2 here. I call this delta x sub 1. I call this delta x sub 2. I call this delta x sub 3. I'll call this delta x sub 4. Because you have 4 intervals, or sorry, 4 subintervals. Oh, I need to be careful with the words I choose. Interval is the whole thing. The subintervals are all the little partitions you do, right? And of course, you know, that was x0. That was x1 right here. That was x2 right here. That was x2 right here, and that was x4 right here. So delta x1 is simply x1 minus x0. Delta x sub 2 is x2 minus x1. Delta x3 is x3 minus x2, and so forth. So again, we're talking about notation here. So delta x sub k in general is whatever xk is minus x sub k minus 1. So remember we said delta x1 was x1 minus x0, right? And notice how those are the same. So in our example, delta x sub 1 was 2 because of width of 2. Delta x sub 2 was 3 because of width of 3, and so forth. So again, I'll draw it again. This is our interval. And again, that was x sub 0. That was x sub 1. This right here, obviously delta x sub 1. And this right here is x2. So that width is delta x sub 2. And this is the part where, okay, you guys are going to have to really kind of bear with me. Now I think the water's getting a little choppy, the air's getting a little turbulent. So kind of, stay with me here. Now we got to create the y values. So we do this by picking any x value in the subinterval to find a corresponding y value that goes with it on the curve. And the usual notation for the selected x value in delta x sub 1 is C1. So in delta x sub 1, that's our first subinterval. That's the width, of the first subinterval. We pick an x value somewhere in between x0 and x1, and we'll call that C1. So I'm going to kind of just randomly do that and call that C1 right there. And then I'm going to draw a line straight up. And the coordinates here will be C1, comma, f of C1. So remember, our curve is f of x, right? The blue curve is f of x. And so at C1 is some x value between x0 and x1. Somewhere in the first subinterval. It could be any x coordinate in the first subinterval. And you get the y value that goes with it, which is f of c sub 1. So the matching y values will be f of c sub 1. And then I would pick something in between 4 and 7 here. So in the second subinterval, pick another random x value. Maybe we'll call it C2. So let me do that. I'll call that C2. So that matching y value would be f of C2. And you keep going until you've exhausted it all, until you've done all the intervals, until you get to f of c sub n. So in our case, for our Riemann sum, let me change colors here. We got delta x sub 1 times f of c sub 1. That's just the first rectangle. That's the area of the first rectangle right there. Then do delta x sub 2 times f of c sub 2. So I'm now doing the Riemann sum, right? The width of the interval times the y value, plus delta x sub 3, f of c sub 3, plus delta x4 times f of c sub 4. So what is this? What am I doing here? that's the area of the first rectangle. So if I draw a rectangle, and the rectangle is going to look like that, because I have to use the y value for the random x value I chose in the first subinterval. And then my next rectangle will look like this. And if I choose, some more, I have those as well. So this right here is now the area of the second rectangle, area of the third rectangle, area of the fourth rectangle. Add them up, that's going to be the area between the curve and the x-axis. Of course, it's a rough estimate because I'm doing 4 subintervals with varying widths and picking my y values randomly within each subinterval. Someone's saying they can't see, it's kind of cut off. Okay, I'll try to move it up. I'm going to go and clear my drawings. And let me rewrite a portion of what I just had. Let me actually undo. Let me select some things and remove. And let me select all this and then move it up. Okay, hopefully you guys can see it better now. Okay, or we could write as a Riemann sum because it's a little cleaner, right? We talk about Riemann sums being a cleaner way of writing your work. So sigma notation. Again, I use K. You can use any letter you want. Maybe don't do X, it's a little confusing. And you're going to do 4. We have 4 subintervals. Delta X sub K times F of C sub K. Or more generally, because we'll have n subintervals, then we'll just say this: K equals 1, n delta X sub K times F of C sub K. Now this is where the waters get extremely choppy, so bear with me here. And this is when I took this, when I took calculus in college, I had professors that kind of were all over the map and were like, whoa, what's going on here? So you might get a little lost here, but if you can follow what I'm doing so far. So again, we have an interval from 2 to 10. We've chopped up into 4 intervals. The widths could be, they don't all have to be equal width. It could be different widths. The y value you choose within each, or sorry, you choose a random x value within each subinterval. You have the corresponding y value, and that's going to hide the rectangle. And again, the technique in which you determine the random x value in each subinterval is random, right? Because I said random. So there's no really set method for picking the y values. You're not doing RRAM, LRAM, MRAM necessarily. And you have all these rectangles and you add them up, and that's the Riemann sum. That's why we do the sigma here to represent that. Now, as I mentioned earlier, we want n to be large. We want n to be large, because if it's large, you're going to have the rectangles are going to start resembling the true area. So there's a new term here called norm. The norm of your partition, piece of partition, is the width of the widest subinterval. So remember, our widest subinterval was a second subinterval. It went from like 4 to 7, right? That was our widest one. So the norm is represented by the norm represents the widest subinterval in your interval. And we write it with these like 4 vertical lines, 2 to the left, 2 to the right, P. It's kind of this weird notation. Ultimately, what you want is you want the y subinterval to get to 0. Because if the y subinterval gets to 0, then guess what? All other subintervals will have the width approach 0, meaning that n will be large, or you'll have infinite subintervals. Because if you're making these tiny, these subintervals, then you're going to have to start adding in more and more subintervals to complete the whole interval or whole partition. This is the big moment. And by the way, in college courses, they even get deeper with the notation and the abstract nature. So that's as abstract as we get. But this is the big moment here. And this is really kind of the crux of second semester calculus. So again, you have a function. It's on a closed interval from A to B. You have a partition, okay? And so you have a bunch of subintervals that you create. And C is just some random X value. So remember, C sub K is a random X value in each subinterval. And subintervals, like you say from like x0 to x1, or from x1 to x2. That's why we have that notation x sub k minus 1, calling x sub k. So this is what we're trying to get at. If you take the limit as the norm approaches 0, so basically when the widest subinterval is getting close to 0, or you could say when the limit as n approaches infinity, it's the same thing. N's number of subintervals, norm p is the length of the y subinterval. Those are interchangeable. And you take the limit of this sigma notation expression, where n is the top, n's a number of subintervals we have, but if you're assuming n's approaching infinity, then you get something called the definite integral. And it's called definite because it is definite. It isn't an exact number. So this is going to be a very specific number, which will represent the area between your curve and the x-axis. And again, why do we care about that? Well, we talked about the other day with like velocity, like if you know you're going at a certain speed, you want to see how much distance you traveled, you'd use a definite integral to get you that distance. There'll be other applications we'll talk about in week 4 that you'll see. So if you look, so basically that's the big moment, is that limit will be something we call the definite integral. And something that we say is integrable. So integrable is the opposite of being differentiable. Differentiable is you take a derivative, other way around, it's called antiderivative, or we call the integral. Question in the chat. It's accurate. So great question that Catherine asked. Is the definite integral accurate? 100% yes. It is accurate. It's not a specific estimate at all. It is going to be the true area. Let me actually incorporate here. We'll represent the true area. So it won't be an approximation anymore. And it's kind of cool. That's just how kind of calculus kind of works out very beautifully. If you look at the conditions you set for the function f when we constructed the Riemann sums, you'll see we didn't restrict it much. This had to be defined over a to b. We didn't even say it had to be continuous, but it does turn out that all continuous functions are integrable. So yes, you do have to have continuity. Well, actually, there are some functions that are not continuous that turn out to be, okay, so that's going to be next week, just so you know. This part right here, we'll talk about that during week 3. Because now I'm getting a little bit too, I don't want to open that can of worms just now. But the bottom line is that if you have a continuous function, you're going to be able to take the integral of it. But if you're not continuous, and it's not guaranteed you can do the integral. You can, but again, let's refrain from getting too deep into that. So this theorem enables us to come up with another definition, one that uses subintervals of the same width. So if your subintervals were the same width, for a definite integral of a continuous function. And it's right here. And this is kind of a big deal. So definite integral of a continuous function on the interval from a to b. So let f be continuous from a to b, and let a to b be partition n subintervals of equal length. And by the way, we talked about how to find the length of the subintervals is you take the difference between the left endpoint and the right endpoint and divide by the number of intervals you want. And if you want those intervals to be of uniform width, the subintervals to be of uniform width, then That's how you compute it. Then the definite integral of f over a to b is given by that limit as n approaches infinity. I did write that. We also used the norm as well, or we did that also, but I like using n, where c sub k is chosen arbitrarily, indicates, so remember, c sub k is an x coordinate, is a random x coordinate in a particular subinterval, and we call it the kth subinterval. So like, so whatever k is, like C1 would be the first subinterval, C2 would be the second subinterval, and so forth. So this is huge. It's a huge deal. So now we're connecting geometry with calculus. This right here was my Riemann sum, right? We can now write it as a definite integral. And that's a notation we use. It's a little squiggly line with A and B. A and B are going to be the endpoints, or we can call these the limits of integration. And f sub k is a specific term. We call it the integrand. The integrand is a function you're actually taking the integral of. Question in the chat. So for Riemann sums, delta x does not have to be equal, but for integrals, yes. Great question that Eleanor asked. You guys are asking fantastic questions. Maybe I'm doing a good job teaching this. I don't know. Or you guys are just awesome students. Maybe both. Yes. The delta x for Riemann sum doesn't have to be equal, right? But when you do an integral, they do become equal. Because what's happening is that you're assuming that delta x gets super, super small when you do a definite integral. So the dx is like delta x, but it's super small, and it's going to be uniform. I mean, what is it exactly? 0.000001, 0.000000, like 1 to the times 10 negative 20th, whatever. It's an infinitely small thing that we just can't get, hard to kind of imagine sometimes. But you have just a gazillion thin rectangles from A to B. That's what's happening. And you want to find that area of the whole thing. Now, how do you say it? Just so you sound like you know what you're talking about. We say the integral from A to B of f of x dx. That's how you say it. Or the integral from A to B of f with respect to x. You can say that too. That's how you would actually say this part right here. Okay. So now let's revisit an example that we did not too long ago. And do some other examples. And then we'll start talking about more, we'll take a more geometrical approach. And I think we'll have time for a break too, because this is pretty intense stuff. So we have found, when we found our, excuse me, our Riemann sum for a function in part 1, this is from like 6.1 actually, the more I think about it. Remember, when we get a different answer for L if we use x. Okay, actually, hold on, let me read it one more time. When we found our Riemann sums for our function in part 1, will we get a different answer for LRAM? Actually, that was in the video, I believe. No, that was sorry, that was section 6.1. My bad. So read one more time. When we found our Riemann sum for our function in part 1, will we get a different answer for LRAM if we use x instead of t along the horizontal axis and our function was y equals f of x instead of y equals f of t? So if I did different letters here, basically. Does it matter? No. the variable you choose is arbitrary. And this is just us as teachers trying to anticipate what questions you guys would have. The variable choose is up to you. Whatever you want to do, you know, it's totally up to you. In fact, we call these dummy variables because they really don't have, I don't know what word to use, but they just don't really mean anything. So yeah, you can do f of x, f of t, f of u, it doesn't really matter. So what does matter is you know what a and b are, you know your endpoints, know what function you're dealing with, and that you understand what the notation is doing. Okay, now let's do some examples. So for the following examples, each C sub k is chosen from the k subinterval of a regular partition of the indicated interval into n subintervals of length delta x. So remember, n is the number of intervals, number of subintervals you have. K is this, subscript we're using. So like C1 would be the x coordinate in the first subinterval, right? P2 would be an x coordinate within the second subinterval. And delta x, remember, is b minus a over n, right? B minus a over n. So that's your a, that's your b. So the question here is just express this as a definite integral. It's really straightforward. You simply just write this 0 to 5. And you're, because you're cubing, you can write as x cubed dx. Remember, C sub k is a random x value, or random x coordinates in a particular sub interval. That's all. Here, you go from 1 to 4. And it's going to be x at 5th power minus 4 over x dx. Here, cosine x dx. Here, 0 to 3, 3 root 9 minus x dx. So that's all. It's not that hard. And there'll be some stuff in the homework we'll have you do, just so you get a habit of writing it, but it's not that hard. Okay. Any questions before we move forward? Because now we're going to start getting into the geometry aspect of things. Great question. Is dx in this case a derivative? Yes, it is. It's kind of a weird thing. It will make a little more sense when we get to next week. So wait till next week. I'll talk more about. Yeah, it kind of is like a derivative. Yes. Another question is, does a larger number always go? Yes, the larger. Well, the number that's to the far right. It's not necessarily a larger number. So this is just going to be your left. Actually, come to think of it. So let me repeat the question. Does a larger number always go on top of the little s thing? So s thing is referring to this right here. Not necessarily. We will see instances when the number up top is smaller than the number down below. But then when that happens, we have to act accordingly. That's going to be a point of discussion tomorrow. So hold on to that thought. There's another question. Why do we use this notation? We use this notation because it is more compact. Sigma notation can get actually, even though sigma notation is compact too, the integral notation is just a little bit easier to write. In fact, actually, when we get to stuff next week and the week after, you'll see why this notation is better than sigma notation. It may not make too much sense right now, but trust me, when we do get to the stuff we do next week, you'll see why we prefer the integral notation over sigma. You guys are asking great questions here. Great questions there. Okay, now let's talk about the geometry aspect of things. So what I'll probably do is maybe I'll do this in example 5, and then we'll take a little break. Then we'll come back and do pages 6 and 7 to kind of wrap things up. Okay, so again, we got some funky curve, right? I'll call this A. We'll call this B. So I'm not being inconsistent, being very consistent here, A and B. And remember, the definite integral, so the limit of the Riemann sums, represents the exact area or true area between the curve and the x-axis. And just to add a little thing, within x equals A and x equals B. So constricted in that region. So if I get a little highlighter out here, so that's what the definite integral is representing. It represents that area. And remember, we're doing all these little rectangles, right? All these thin rectangles in between. In fact, I can even show you one of those rectangles. And you can call this delta x. And the height, you can call f of c sub k. So so in this case, if f of x is non-negative, so it's above the x-axis. If you're non-negative, so you're above the x-axis, and you are integrable. Remember, if you are all continuous functions are integrable, then the area under the curve can be written like this. So that represents the exact area, the definite integral. We made that connection already with the Riemann sums. That was a geometry calculus connection, right? That we just talked about 10 minutes ago up here. Okay, so now let's actually use this to find the area. So when you're asked to evaluate the area of this, what that means, let me do this as a text box. This means that we must find the area of the region enclosed by y equals square root 9 minus x squared and the x-axis x equals, is that 0.3? That should be -3, by the way. Let me get it off the text box now so you guys can see what I typed. Okay, so we are lazy as mathematicians, so that's what this means, right? So that's why we have all these notational things. There's one thing that we do often in Algebra 2. I'm trying to think here. What am I thinking about? It's dealing with, gosh, it's an old school concept that we deliberately write compactly. It's just, okay, it'll come to me. I don't know. But, you know, that's just what all that means, because mathematical language could seem like Greek to a lot of people, or seem very complex. But what this means, by the way, that's -3, is just give me the area between the that function and the x-axis within -3 and 3. So what I'll do is I can make a little table. If I were to plug in -3, I think I get 0. If I were to plug in 3, I would also get 0. If I plug in 0, I think I get 3. So you wind up getting a shape. What shape do you guys think this is? Someone could put into the chat if you like. It's not an inverted parabola, actually. It's actually a geometric shape that you guys have seen a long time ago. It's a semicircle. Yes, it's a semicircle. So this is a semicircle. And why is that a semicircle? Because if you were to say y equals √9 minus x squared and square both sides, you get the equation of a circle. That's why. So what's the area of a semicircle? It's 1/2 pi r squared. Well, what's your r? 3. So the answer to this is 1/2 pi times 3 squared, or 9 pi over 2. So when you see that, draw the graph, see what shape you got, use your knowledge of geometry, and work it out. That's all. So again, that's what I'm saying. This is a geometry calculus type of connection, this definite integral. That's really what it is. Now, there will be times where it's hard to tell what shape you have. That is going to be the point of discussion next Monday. Next Monday is called the fundamental theorem of calculus. Sounds very important. It is. I've never taught it in one day. I will. We'll see how it goes. But yeah, that's what we're going to cover next Monday. It's something called the fundamental theorem of calculus. When the shape is not necessarily geometric and you have to do something else. In fact, I'll tell you what we're going to do. We're going to do antiderivatives. And there's a technique for antiderivatives I'm going to teach you guys next week. As opposed to just looking at by, intuition. But yeah, just 9 pi over 2 is the answer for this one. So it's just area. That's all we're doing. So this might be a good place to take a little break right now. And then we'll come back in about, let's say, so it's 10:07. Let's come back at 10:17 or 10:18. We'll do more of these notes here. So we'll do pages 6 and 7. And then we'll see where we are after that. Okay. So I'm going to go ahead and clear the screen here. Let me stop sharing, and I'll stop this recording.